Up to this point in our studies, we have analyzed 1D structural members under different loading cases: axial loading, bending, and torsion. However, in reality, most engineering structures and components experience a combination of these loadings. Hence, they experience more complex stress states. How can we predict where and how failure will occur? From your studies of the materials component of the course, you are aware that certain materials, such as ceramics and some high-strength metals, are brittle. These materials typically fail due to a critical level of normal stress, which cause material planes to separate, which results in cracks to initiate and propagate until the part fails. On the other hand, many metals exhibit a more ductile nature, creating permanent plastic deformations. These materials fail due to the movements of dislocations in the crystal lattice, which are initiated and controlled by shear stresses. In order to determine which types of stress are present in the member and in what directions they act, we need to develop new analytical methods which look at the general stress state at a point. Here we have an infinitesimally small material element in our member with 3 orthonormal faces perpendicular to the Cartesian coordinate axes x, y, and z. On each of these faces we have a stress acting normal to the plane, sigma x along the x-axis, sigma y and sigma z along their axis also. Along each face we also have shear forces, which are denoted by 2 subscripts. For example, on the x face we have tau sub xy. Here the first subscript denotes the axis perpendicular to the face, x in this case, while the second index indicates in which direction the shear stress is acting, along the y direction in this case. Likewise, tau sub xz is also normal to the x-axis and acts in the z direction. We have the corresponding shear stress configuration on the other faces. This means we can describe the stress state acting on this element with 9 components, 3 normal components, sigma x, sigma y, and sigma z. We also have 6 stress elements. However, we can reduce the number of independent shear stress components using shear stress reciprocity. If we look down the z-axis of our element, we can see one face of the element and the stress is present. We have the sigma x acting normal to the x-axis on both sides, and likewise sigma y normal to the y-axis. We can also add our shear stress tau xy and tau yx according to the previous diagram. We assume the side length of the element in the x and y direction is dA. We can then perform statics on this element, but first we need to be able to find the forces, which are calculated as stress times area. For this we will assume the element has an out-of-plane thickness of 1 in the z direction. The sum of forces in the x direction must be equal to 0, which gives us sigma x times dA times the unit thickness of 1 minus x dA times 1 from the other side. Likewise, we will get the same thing for the components of force from tau yx, giving us the trivial result that the sum of the forces in the x direction is 0. If we look at the sum of the forces in the y direction, we get the same trivial result. If we now formulate the moment equilibrium about the z-axis, we will get no contribution from sigma x and sigma y as they pass through the z-axis. However, tau xy and tau yx will form couples around the z-axis. This will give us tau xy times dA times 1, which is the force multiplied by the moment arm, dA, as a moment in the positive z direction. The moment created by tau yx is tau yx dA times 1 multiplied by dA, which is acting in the negative z direction. If we cancel all the common terms, we end up with the important relation that the magnitude of tau xy is equal to tau yx. This is the so-called shear stress reciprocity. You can do the same analysis for the other phases, and you will find that the same relations hold for the other shear stress components. So tau xz equals tau zx, and tau yz equals tau zy. Hence, due to the shear stress reciprocity, we can now describe our general stress state acting on our element at any point in a solid by 6 components: 3 normal stresses and 3 shear stresses. This description of the general stress state in a material is a very fundamental characteristic of any solid and also fluid mechanics analysis. However, for the purpose of our studies in this course, we focus on a special, technically very important stress state, the state of plane stress. In a state of plane stress, one area element is stress-free, as shown. There are all stress components related to this area element are 0. This means that we can now describe our stress state by 3 components: the 2 normal stresses, sigma x and sigma y, and 1 shear stress tau xy. Plane stress is technically important for 2 main reasons. The first is when we analyze stress states close to a free surface of a structure, which is clearly one of the most common practical cases. If no forces or stresses are acting on the surface, it can be analyzed by a plane stress state configuration. The second case is the analysis of thin-walled structures, such as thin-walled pressure vessels, composite laminates, as well as plate and shell structures, where the thickness is much less than the in-plane dimensions. These structures can also be analyzed using a plane stress model. After we have introduced the framework of the possible stress components that may exist at a point in a structure, we can now start looking at how we can analyze a stress state and identify the magnitude and direction of critical stress components that may result in the failure of a material or structural component.